Today, I start to discuss really in depth renormalization theory. It's a bit too high, the sound. For Phi-4. So I just started to discuss the fact that the physical mass is different from the bare mass, which is in a naive calculation present in Phi-4 theory at one loop. So we are going to discuss this effect in more detail and see how it solves the problem of ultraviolet singularities. So this is renormalization theory. So I'm going to discuss the Phi-4 theory. I'm going to stay in an Euclidean setting because that's what I started for, but in fact, there is no difference in the discussion between the Euclidean theory and the theory at real time. So just for simplicity, I treat the Euclidean theory. I'm going to discuss the theory in perturbation theory at one loop order. So this is the first order in the semi-classical expansion. And I'm going mostly to discuss the case of the massless. Well, today I'm going to discuss the case of the massless theory because that's the most important case and that's where you see already all what's going to happen. Considering the massive theory makes things a bit more complicated, but the basic idea are in the massless theory, and the massless theory is very important in itself. Okay, so what I'm going to do first, I just make reminders of the structure of perturbation theory. That's what we did yesterday. Then I'm going to discuss the presence of ultraviolet divergences. And then I'm going to discuss mass renormalization. That's something we discussed on a very crude level yesterday. The coupling constant renormalization, which is very important. And then, if time, the issue of renormalization scale. And the so-called beta functions. Okay, no, I'm going to explain all what this is, but I think you already have met some of this concept in the statistical mechanics course in a different framework, but you'll see the parallel in the next lecture. Okay, so perturbation theory. So let's explain. We start from a Phi-4 theory. So its naive action is S of phi. This is a classical action in integral d dx 1/2 of d mu phi squared plus m squared over 2 phi squared plus g over 2 phi 4. And I want to construct the quantum theory out of its correlation function. So the expectation value in the vacuum of products of operator. And they are defined in my framework by a path integral. So I have a path integral, which is basically something which is d phi exponential of minus s of phi. Okay? So for simplicity, I set h bar equal 1. Because we have seen that the expansion in h bar is just an expansion in terms of the number of loops of a Feynman diagram, which in itself is related to the number of vertices in the coupling, in the graph. So expanding in h bar is the same thing as expanding in G. Okay, for simplicity. Okay, and then, so out of this object, we construct correlation function. Green's function, vacuum expectation value operators. Yes?
Don't we usually put 4 factorial there?
Pardon?
Don't we usually put 4 factorial there?
Yes. Thank you. Thank you very much. This was a morning typo of mine. Okay, thank you. Okay, so now, as we have seen already yesterday at the end of the lecture, the physical mass is not equal to the mass we had in the classical action, because simply an effect of radiative correction, some very standard quantum effect. So it's not obvious that the action you must take in a path integral is the one which contains the physical parameter to be measured or to be defined. So I'm going to change a bit my rule. I'm going to change the rule by taking arbitrary parameter here, A, B, C, which for the moment are arbitrary. And at the classical level, A is 1, B is m squared, this is a mass, and C is a coupling constant. Okay. But we are going to see that renormalization requires the receipt to be modified. Okay? And we have seen then that, well, if we use the classical action, we can compute the two-point function, and out of the two-point function, I can compute the irreducible two-point function, which is given by this diagram. It's a truncated, the doubly truncated propagator plus G times 1/2 times this diagram. And that's it. At first order in G, at one loop order. And the 4-point function that I've not drawn yesterday, but which is first the interaction vertex, okay? And then there is a, which is proportional to G, of course, because there is a G factor. And then we get one loop diagram, which are proportional to G squared, because they contain 2 vertices. And here are the 2 diagrams. The first diagram is this diagram. Okay. Then the second, so let's call this the vertex 1, 2, 3, 4. This is vertex 1. Well, in my notation, that's rather this. I go clockwise, anti-clockwise. So this is 1, 2, 3, 4. And then we get the same diagram where you have here 1, 3, 2, 4. Okay. And the same diagram where the amplitudes here, the external legs are 1, 4, 2, 3. Okay. And each of them has a factor of 1/2. That's a symmetry factor. Okay, etc. Okay. And now to this, of course, these are functions of either the external position or the external momenta. And in Fourier transform, the Fourier transform of this, so if you want in momentum space, which is the simplest way to analyze, here we have a momentum P that enters in here, okay? So that this object is P squared plus M squared plus G 1/2 this function T of M, where T of M is integral d dk over 2 pi squared 1 over k squared plus m squared. Okay? And similarly, this in Fourier space, there is a momentum P1, P2, P3, and P4, which is minus P1 plus P2 plus P3 by momentum conservation. So if I get rid of the delta function that I wrote explicitly yesterday, this is going to be G, just this is the contribution of the vertex. It's independent of the incoming momenta because it's a point-like interaction, it's a contact interaction. But these terms just represent the interaction between two bosons via the emission and absorption on virtual particle. That's a radiative process. It's going to depend on the momenta. And this is going to be minus G squared 1/2. And it's clear here that it's a function of the sum of the incoming momenta. So because this is going to be a function that I'm going to call B in my notation, which is B of P1 plus P2. That's the total momenta that enters here. And of the mass, okay, plus the same function of P1 plus P3, the mass, plus the same function but of the argument P1 plus P4 and the mass. Okay? And this function B is just let us write it here. B of some incoming momentum P and the mass is just given by the amplitude of this graph where you have some incoming momentum P here. So the Feynman diagrammatic rules mean that here you have some internal momentum K. Here you have some internal momentum P plus K by conservation of the momenta. And so that the outcoming momenta here is P. And the amplitude of this is a product of the propagator for this internal line and this internal line. So it's 1 over k squared plus m squared times 1 over p plus k squared plus m squared integrated over the internal momenta normalized by 2 pi d. So this is the amplitudes of this diagram in momentum space. Okay, yes?
Those vertices have like 3 branches.
No, that's simply because here these amplitudes have 4 branches with momentum P1 coming inside and momentum P2 coming inside, but that depends only on the total momentum P equal P1 plus P2 that I'm going to call P. Because if here you have momentum K, if here you have momentum P1, and here you have momentum P2, here you have momentum P1 plus P2 plus K. And it's easy to see that it depends only on the sum of the momenta, because the momenta merge at the vertex. So that's why this is a function of P1 plus P2, this is a function of P1 plus P3, and this is a function of P1 plus P4. Is it clear? Okay. Good. So of course, you have to compute those functions, but so we have the function, the integral t, we have the function b, and now, of course, well, I'm going to consider the theory in dimension 4, because that's an interesting physical case for many reasons, and that's where renormalization has to be taken seriously. So let's consider the case where the dimension of space-time, or here of Euclidean space-time, is 4. Okay. Here, so K is a 4-dimensional vector, P is a 4-dimensional vector. Okay. So you see in this case that both integrals have divergence at high momenta. You see. So T of m in this case, T of m is integral d4k divided by 2 pi squared, 1 over k squared plus m squared. Okay, and it is clear that it's divergent at high momenta, because at high momenta, it's a d4k divided by k squared, so it's divergent, like the square of the momenta. It's quadratically divergent. So let's introduce a sharp ultraviolet cutoff by assuming that in these integrals, the internal momenta are always less than lambda, where lambda is some regulator in momentum space. So it's a very high momentum space. It's much bigger than m, or it's much bigger than the momenta we are considering here in the external momenta. So k is going to be much larger than m. I'm sorry, lambda is going to be considered as always much, much larger than m, and much, much larger than the modulus of the external momenta. External momenta in the problem. Okay. Then you see that this integral diverges at high momenta. So if I define that this depends both on m and lambda by introducing this regulator, it's diverged like lambda squared at high momenta. When I cut off this integral, it's an easy calculation, it diverges like 1 over lambda squared. And with a bit of work, the coefficient in front is 1 over 4 pi squared. That's just an easy calculation. You go to radial coordinates. You take into account the volume of the three-dimensional sphere, and you get this result. Okay? So this is a leading term. And the leading divergence doesn't depend on m, because k is much, much larger than m when it's of order lambda. Now, there is the integral depends on m, which means that there is another term that depends on m. There are corrections to this, subleading correction. Okay? And you can check that the subleading correction is a log of lambda squared, but it has to be proportional to m squared, and there is a minus sign. So the leading divergence is quadratic, leading divergence, and the subleading divergence is logarithmic. Okay. And you can get this subleading divergence simply by making a power expansion of this into 1 over k squared minus m squared over k squared squared plus higher order term. So you expand this in powers of 1 over k squared at large k. So you see that the leading term behaves like d4k over k squared, which gives a quadratic divergence, and the correction gives a d4k over k squared squared, which is a logarithmic divergence. It behaves like dk over k, hence the log. Okay. Then you have term over the 1 when lambda goes to infinity. So this is an expansion when lambda expansion when lambda goes to infinity. Okay? So there are ultraviolet divergence in the two-point function. This is ultraviolet divergences. Okay. So now let's go to this function b. This function b depends on p. So this is for t. Now let's go to the function, to the diagram like this one, which is given by this function B of P, M, and now I introduce a cutoff. So I introduce a cutoff, which means that when K is larger than lambda, I replace the propagator by 0, and in order to be consistent, if P plus K is less than lambda, I replace the propagator by 0. So I replace this by an integral where K is less than lambda, but P plus K is also less than lambda, so that it's a symmetric integral. It doesn't depend on what I call K, what I call P and K. Okay, so then it becomes a function of lambda. Okay, so now you expect that it's going to diverge logarithmically if we're in 4 dimensions, because we have d4k divided by 1 over k squared times 1 over k squared. When k is much larger than p and m, it's a dominant term. So we expect a log of lambda. Okay? In fact, a log of lambda. I'm going to write a log of lambda squared. Okay? And you can expand. You can guess what it is because it's d4k over 2 pi to the power 4, 1 over k squared. So it's the same divergence as the divergence of this term. So the coefficient, once you do the calculation, is again 1 over 4 pi squared in 4 dimensions. And then you get term for the. So you see the leading divergence, the leading divergence when lambda goes to infinity is a log. Okay? And you see that the leading divergence doesn't depend on P or M because it's a divergence that occurs when K is very, very large, much bigger than M and much bigger than P, so you can neglect them. So it is independent of P and M. And again, here, this one is also independent of P and M. That's going to be quite important. Okay. So this was the second backflow. This was the first one. This was just a continuation of this one. Okay. So when you introduce a regulator, a cutoff in momentum space, you see the divergence that comes from the short distance behavior of the propagator. So remember, this comes from the fact that the propagator in momentum scale behaves like 1 over k squared. So this comes from the fact that G0 of k behaves like 1 over k squared, which is equivalent to the fact that in momentum space, G0 of x minus x1 minus x2 behaves like x1 minus x2 to the power 2 minus d. So this was minus 2 in d equals 4. So it has a singularity. Okay, so this divergence comes from the short distance singularities of the quantum field operator phi of x. Okay, so it's something that is particular to the fact that it's a quantum field theory. Okay. Good. So now let's end up for discussion of ultraviolet divergence. I'm going to discuss some other way to regularize the divergence later on, I think, when discussing the general strategy. But let's go back to this particular case of the phi-4 theory, 1 loop, 2 and 4 point function. Okay. Then we have seen already that from the explicit expression of the 4-point function that the physical mass of the theory is not m. Okay, physical mass. So let's go. Oh. The physical mass m physical is given by m squared in this expression plus g 1/2 T of m lambda. This expression which is divergent. Okay? There are radiative corrections. Of course, there are going to be higher order correction in G, but I'm working at first order in G, one loop. Okay. So it means that if I am interested into a theory whose physical mass is 0, then this has to be equal, this plus this has to be equal to 0. Okay? So this means that we must introduce in the action what's called a counter term. So this means that if we start from a theory that is classically massless, so we start from a theory that is classical theory massless, so that on the classical action I start from my coefficient b here is 0. When I plug in the interaction, or if you want, I plug in h bar, I plug in the quantum mechanics, because remember, G comes with h bar. I have to add to B a term which is minus G 1/2 T of the mass, but this here, this is going to be the classical mass, which is 0, so T of 0 and lambda plus higher order terms. You see? With T of 0 given by this, with T of 0, T of 0 and lambda is just 1/4 pi squared times lambda squared. Okay, because if the mass is 0, this term gives 0. Okay. So we must introduce what's called the counter term of mass associated to the phi-4 term. You see, we must take in our original action B not to be 0, what it would be if the theory was a classical theory, but we must change it by this term. Okay? Okay. Yes?
So when in last class we derived this expression for the physical mass.
Yes?
And we got that it's
yes.
m squared plus the correction with G over 2T.
Yes.
And why are we putting a 0 now and not a B?
A V?
Inside the T?
Pardon?
Inside that T.
Yes?
Why are we putting a 0 and not a B? That is the, if I perform the same calculation as yesterday, but with that action,
yes.
A, B, C,
yes.
wouldn't I expect to have a B inside of it? Or square root of B?
At the moment, no.
Because I want up to order G or something like that.
I'm working at order G. So do you agree that if I take an action, so let's go back. So now let's try this. So now the recipe is that for a massless theory, Well, that's going to be a bit messy. Let me just summarize what we are doing. So, for a massless theory at the moment, well, let's write it. We are taking that A equal 1, B equal 0 plus 1/2, plus G times minus 1/2 1/4 pi² lambda squared, okay, in our action. And with this choice of B, the theory, the quantum theory, is massless at one loop. That's all what I want, okay? If I had taken here an m squared different from 0, then the classical theory would be massive, whatever I do that here. Because when G goes to 0, classical theory is massive. So I want to start from a classical theory which is massless, and when I plug in the interaction, or plug in h bar, the theory stays massless. Okay. So this is from massless. Okay. So now, we have to treat the renormalization of mass, of the coupling constant. Because we see from this calculation that now for my massless theory, the 4-point irreducible function, okay, in momentum space is G minus G squared 1/2, and a function that contains, we computed them here, logs. Yes?
So we estimated B and T for big lambda, right?
Yes.
But in that calculation, didn't we assume that the mass and the coupling constant are independent of lambda? Because now you're going to have a mass which is like going to blow up as well.
Yeah, no. Here, B is not independent of lambda.
Yes, I know.
I'm adjusting B.
Oh.
So in this calculation, M has disappeared. You see, the parameter M has disappeared.
What you called mass before. So before you calculated like D of M and lambda and B of M and lambda. B M and lambda.
Yeah.
But that M is now replaced by square root of B.
No. Here now I get rid of the mass. I'm just speaking of physical mass, which is 0, and this coefficient B.
Why is the physical mass that M? Isn't that M?
No. Well, I started by a naive M, but now I'm treating a theory where I enforce the physical mass is 0. Okay? And in order for the physical mass to be 0, the coefficient B in the action in the path integral, in the functional integral, has to be taken of this form. Okay? Do you agree with that?
Yes.
Because then the 2-point function is p squared. It has a 0.
So my point is this.
Yes.
You first wrote down just
Yes.
normal lambda phi form.
Yes.
Yeah.
Well.
With a mass.
Yes.
That you call
Yeah.
M.
Yes.
And then you calculated D.
Yes.
With an M in there. But that was the M from the action.
Yes.
Not the physical mass, but the M
Yeah.
from the action.
No, but now I take the action that is written up. So it contains the coefficient in front of phi squared is denoted B. Okay?
Yes.
So you can say that it's a mass. You can think of it as a mass.
What does that mean?
Because it's just a term proportional to phi squared
Yeah, but
in front of
what
it.
does
But
mean
it's not the physical
when you
mass.
think of it as what is a physical mass?
The physical mass is 0.
No, what is a physical, what does that mean, a physical mass?
I took as a definition of the physical mass the zero in momentum space of the two-point function. Okay? That's what I explained yesterday.
That gamma, that theta.
And you see that here, the two-point function with this choice of physical mass is just p squared. So with this choice, with this b, you see, with this b, the irreducible two-point function as a function of the momenta is just p squared. There are no one-loop correction anymore, so this is 0. And then you get something of order g squared. So it has a 0 at p squared equal minus m physical squared, which is 0. So the 0 of this function by the Chelan-Lehmann representation theorem gives you the physical mass of the theory. The Chelan-Lehmann theorem that you have seen in QFT1. Pardon?
Monday's tutorial.
And there was a tutorial too. It states that if you consider the inverse of the two-point function, which is the propagator of the theory, the full propagator, G2 of P, as a function of P, in any quantum field theory, reasonable unitary quantum field theory, it can be written, if I am not mistaken, as an integral from 0 to infinity. As there is something like d mu. You have 1 over, with my notation, it's going to be 1 over p squared plus mu times the density of state rho of mu. That's this form. Where when the density of states, so mu is something like an energy squared. And you see, this function rho has a delta function at the first state of the theory, the first excited state of the theory, so which has a mass m squared. That's the mass of the first one particle state of the theory. Then you have at 4 m squared a continuum, which are the energy of the states containing 2 particles or 4 particles, so they are necessarily larger or equal to 2m squared, because this is a state that has 2 particles of mass m plus some kinetic energy. And then eventually, if the theory has excited states, so bound state of these particles, they have a higher mass particle here. So you see that when you write this, the first contribution of this is the contribution of the pole. So you get a 1 over p squared plus m squared, plus the contribution of higher order of the continuous spectrum, which gives something which is analytic on p squared equal m squared. So this theorem tells you that G2 of p squared as a function of the p squared has a pole in p squared space hat p squared equal minus m squared. And that's what we get here, because here we get that from G2, the two-point function of p is just 1 over p squared. So it has a pole at p squared equals 0. Hence the mass of the first excited state is here at 0. Okay? Yes?
I don't quite understand why there is no contribution at first order for the two-point irreducible function.
That's because we've adjusted B so that the pole is at 0, and that's because the first contribution, the contribution of the radiative correction in the 5-4 theory to the mass to the two-point function are just a constant. They are independent of P. You see? So it's something which is different from, for instance, from QED. In QED, this is a propagator for the electron, and then the E squared term is given by this. So this contains a log lambda singularity, divergence, but it depends on P. So even if you adjust the mass, if you consider massless quantum electrodynamics with massless electrons, massless fermions, okay. Then because of some symmetry, you don't have this, well, there is some, because of some chiral symmetry, you don't have a divergence, but you still have something that depends on P. So if the mass is equal to 0 for the electron, then you get a contribution over the E squared, the coupling constant or alpha, but you get something that depends on P, on the momentum P, in QED. But that's because this diagram, the momentum P flows in this loop, so it depends on P. So in phi-4, it's a particular aspect of phi-4, and this diagram does not depend on P, on the momentum. So it's a very special property of phi-4. Okay. The important point is that we want this to be finite and to be 0 at P equals 0. If it's 0, that's the better. Okay. Okay. Okay, so now renormalization of the coupling constant. So I'm going to consider now this theory where I keep A equal 1. B is given by this, this solution. Let us box it. It is important. But then I keep, so B is fixed, because we have renormalized the mass. But let's keep the coefficient C not fixed yet, okay? Because we have seen that the action can be different from what we get. So now, what do we get? So here in this calculation, I just replace G by C in my calculation. So the irreducible 4-point function is just first the coefficient C, because I have replaced the coupling constant in the action by C. And then I have the contribution of the two-loop diagram. This is 1/2 C squared, and then I get the amplitudes of P1 plus P2. The mass is B, and I have a cutoff plus the 3 other contributions obtained by replacing P1 plus P2 by P1 plus P3. Okay? So let me write this B of P1 plus P3 B lambda plus B of P1 plus P4 B and lambda. Okay? And with this theory, the 2-point function, the irreducible 2-point function, remember, now I deal with an action where C is arbitrary. So the 2-point function is P squared plus nothing. Okay? Something of order c squared. And B is given by minus 1/2 1 over 4 pi squared lambda squared times my coupling constant, which is now C. Okay. So now this is an expansion in C, and B depends on C. Okay, B depends on C and lambda here. But B appears only here. But you see, B is of order C. This term is already of order C squared. So if you consider that this is an expansion in C, you can replace B by 0 because the correction will be of order C cubed. Okay, so I can rewrite the 4-point function as, so B is of order O of C. So I can replace the 4-point function, the irreducible 4-point function, by C minus C squared 1/2 B of P1 plus P2 0 lambda plus the two other terms that are obtained by permuting the momenta. Okay? So this function is just the amplitude of this one loop diagram I draw here. But when the mass in the propagator is set to 0. So B of P1 plus P2, 0 and lambda, is just the amplitudes of this diagram with an internal momenta here, P1 and P2. So it depends on P1 plus P2. And here the propagator here is 1 over k squared. And here the propagator is 1 over P1 plus P2 plus k squared. Okay? So these amplitudes, well, I have 2B. That's a very bad notation, in fact, I realize. Sorry. So think about this, well, let's call this B with a boldface. Yeah. Okay. This is the amplitude of the diagram. Okay. Is it clear? So B and C are just numbers that appears in the action. Okay. So this amplitude is ultraviolet divergence at here. You see, it contains a log divergence. Okay. So it's 1 over 4 pi squared times log of lambda squared. Okay? But now it's a function both of lambda and of the external momentum. And we know that it's a dimensionless integral. It has a dimension of an integral over 4 momenta divided by momenta to the power 4. So it's a number, it's a pure number. It doesn't have any dimension. And it's diverging like a log of lambda squared. But we cannot have a log of a momentum. Logs are defined only for dimensionless number. know what is log of 1, log of 2, log of 10, but we don't know what is the log of a meter or the log of a kilogram. Okay. So this means that this lambda squared has to be divided by another something, another quantity which has a dimension of the momentum in order for this expression to make sense. And the only other expression that we have, which has a dimension of a momentum, is the momentum itself. So this has to be log squared divided by the square of P1 plus P2 squared. Okay? So forget about this with a Chern-Lehmann theorem. Okay. So, yes?
So then what do we do with the term that we had in the T m lambda?
This one?
Yeah.
This one?
Yes.
Yeah.
The log that we have there.
This would become T of B and of lambda.
Yes.
Okay. So here we would have a B log lambda squared. But B is over the C. So this term is over the C, while this term is over the 1. So this will play no role at order P in the two-point function. Yes?
Okay, but
yes?
But we have to deal with the same thing about the dimensions of the log of lambda squared. We divided by an
yes, you are. No, very good remark. I wanted to hide it a bit under the carpet.
Sorry.
No, but it's not a problem. Here is the same. In fact, it's a log of lambda squared divided by something which has a mass dimension of a momentum. So it's a log of lambda squared divided by m squared, in fact. So in the term over the 1, there is a log of m. You see. But m squared times log of m goes to 0 when the mass goes to 0. So log of m could be, you could think that it gives rise to what's called an infrared divergence, a divergence when the mass goes to 0. But m squared log of m goes to 0, while log of m doesn't go to 0. Yes?
So what I was objecting to earlier is that in there you have a T of m lambda, right? But now we're not actually working with an m anymore, we're working with a b.
No, I'm working with A, B, and C.
Yes.
Okay.
So what's there is actually the function d of b and lambda,
Yes.
where b goes as lambda squared,
Yes.
which means that there's a 1 over k squared plus b now,
Yes.
and again b goes as lambda squared. So you can't say that b is a lot smaller than k squared anymore for k big.
Yes. In fact.
So the expansion you made
Yeah.
isn't actually valid anymore. You're assuming that m over k is very
Okay.
small, but it's not
Yeah.
anymore.
I am assuming that C is small enough so that lambda squared C is small.
Yeah, but it's not an expansion if for lambda being big. It's at best an expansion for g being small or something.
Yeah. So in fact, well, wait a minute. You'll see that I'm doing this kind of calculation, assuming that I'm expanding in C. I'm sorry, I should write this here. I keep lambda fixed. I expand in C, and then I let lambda goes to infinity.
Okay.
You see? So I agree that this is not completely consistent. But let's take this as a receipt, mathematical receipt. Okay? Then we are going to discuss from the results when is this consistent or not. Okay? So we have two limits. We have the limit when the h bar goes to 0. If you want, if you think of it in terms of a semi-classical expansion, we have two limits. We have h bar goes to 0, which means the loop expansion. Because basically what I'm doing is that keeping graphs at a given order in loop expansion. And then I'm going lambda goes to infinity, what's called the continuum limit. Okay. And what I'm doing is that I'm first doing a loop expansion and then doing the continuum limit. But you might object that this is not what should be done.
Yeah, no, my point is just that what you're heading down there is an expansion in like m over k, for k big, so something like m over lambda.
Yes.
Which doesn't actually go to 0 if you take lambda to infinity. You need to take c to be small.
Yeah. No, but that's what I'm doing. First, I'm assuming that lambda is big but fixed. I expand in C. I keep the term of a given order in C. And then I make lambda goes to infinity. So you are right in asking the question. And the real answer is that we are applying this recipe. We see that we get consistent result. And then later on, we are going to discuss whether this limit commutes with this limit. But this question is a difficult question. So the answer to this, so if you say question, those limits commute. Okay, and the answer is this requires a renormalization group analysis that I'm going to do later on. This requires an analysis, a non-perturbative analysis of the running complete constant. So wait a little. At the end of this lecture, or rather next lecture, we'll discuss that.
So if that's an expansion in C being small.
Yes, that's what I stated.
O of 1, because lambda's for example, the first.
No, here it's a O of 1 in terms of lambda. What I mean, plus term over the terms of order 1 in when lambda goes to infinity. So
you're not making an expansion in lambda being big. You're making an expansion in C.
No. This is a function of lambda. There is no C. When I said write O of 1, it means that when lambda goes to infinity, you have log of lambda, and then you have terms which are finite or going to 0 when lambda goes to infinity. So this is not a statement about the expansion in C. This is just a function of momenta and lambda, the mass being fixed and the momentum being fixed. Okay?
Maybe we should just talk about it.
Yes. I prefer. But your question is very relevant. But for the moment, I'm doing this. Okay? Good. So let's possibly keep this around and go to this. Okay. Okay. Okay, so you see that if I compute the amplitude of the one loop diagram in the presence of a cutoff but with 0 mass in the propagator, this is just a simple function. It's a log of lambda squared divided by p squared. And well, I gave a very simple dimensional analysis, but you can do the calculation explicitly, and you'll check that there is this log of p squared plus m squared. So that's just a simple way to recover that. So this result is very important. Okay. So now, with this calculation, the irreducible two-point function is just, let me rewrite it again. So it's a function of the momenta P1, P2, P3, and P4 with P1 plus P2 plus P3 plus P4 equals 0. And it's given by C minus, and with this calculation, what I get is that I get C squared 1/2 1 over 4 pi squared times log of lambda squared divided by P1 plus P2 squared plus same thing with 1,3, same thing with 1,4. Okay? Good. So this is the value of the irreducible 4-point function as a function of the incoming momenta. Those are truncated legs. And P1, P2, P3, P4. Okay. So now, in the same way that I have defined the physical mass, so the physical mass in this theory is equal to 0, so that in fact this depends only on the ratio of lambda squared divided by p squared. You see that this contains short distance divergence. Lambda goes to infinity divergence. But now you have to think of the fact that the 4-point function is a way to calculate the physical coupling constant. Because, for instance, through the LSZ reduction formula, out of this truncated 4-point function, you get the collision amplitudes for a process where we have two incoming particles, a collision between two incoming particles, and they get. So out of this 4-point function, you get, for instance, the scattering cross-section, total cross-section, for a process where you have two incoming particles, they hit, and they, for two-body process. Okay. And remember, this is a theory where you have particles that have a contact repulsive interaction. So they behave like quantum marbles, ball. Okay. So the value of this scattering cross-section give access to the strength of the interaction, of the repulsive interaction. Okay. So the strength of the interaction between particles in the quantum theory, you can extract it from this calculation or from this measurement. Okay. But now you see that in this expression, since our theory is massless, there is no preferred momentum scale. Okay. So in order to define what is the strength of the interaction, okay, which this is a word, okay, we are going to measure it by a quantity that we call the renormalized coupling, and that I'm going to call GR, R for renormalized. Okay? In the same sense that the renormalized mass was 0, we are going to define the renormalized coupling. And I'm going to define it with reference to a chosen momentum scale that I'm going to call mu, okay, which correspond to the energy scale at which we, par exemple, perform a scattering experiment. Say, if you have massless particles and you make scattering of them, for instance, you accelerate photons, let's say, and accelerate them and make a collision, or massless electron, or simply if the energy is very, very much higher than the mass of the particles. If you do electron-electron or electron collision, positron collisions at very high energy. You can treat them as massless particles. But you have to specify what is the energy of the particles. Okay. So I choose a momentum scale that I'm calling a renormalization scale. Okay. And here I make the following choice. Here my choice is that I choose a choice of momenta such that P1 plus P2 squared equal P1 plus P3 squared equal P1 plus P4 squared equal mu squared. Okay? So that's a choice. I could have chosen something else. And then, so I make the choice, and then I define my renormalized coupling constant in my theory, defined by the action with A, B, and C, as the value of the irreducible 4-point function, okay, for this choice of momenta. Okay, so let us call this some reference renormalization R. So this is a choice of a reference point in momentum space, of a renormalization point in momentum space. And for the specific value of this momenta, in the node they are called P naught, I think, but here let's call them P naught. The value of the 4-point function is by definition, so this is a definition, the renormalized coupling constant. Okay? That's it. So that's what I'm going to call the renormalized coupling. So that the strength of the interaction measured or calculated in the theory at an energy scale mu. Okay? And with this choice and this formula, of course, what we get is that GR squared, GR is C minus C squared, 3/2, 1/4 pi squared, log of lambda squared divided by mu squared. Okay? Yes? Hello?
It's okay, carry on.
You are just visiting. Welcome. You want to join? Yes?
No, what are you choosing first? Are you choosing the mu first and then like getting the moment out of it, or?
No, I am choosing mu, and then I am choosing a momenta which satisfies this condition.
So mu is already fixed.
I choose mu, and then I choose P that satisfies this condition. Well, in 4 dimensions, there is still some flexibility in choosing the P's. But if you were, for instance, in 3 dimensions, since the P satisfies, that the sum of the P's has to be equal to 0, then this would fix the P to be the submit of a tetrahedra with a size mu. So this fixes almost all the mu's. Yes?
So I know it's just a choice, right?
Yes.
We can ask for that.
Yes.
Like when we started doing the calculations, I don't know, I thought about that diagram, for example, and P1 and P2 and P3 and P4 just only had to satisfy the condition that
yes.
some of them is
yes.
that condition.
Yes. So this is a general condition that's yes. satisfied by translation invariance.
Okay, and how is that I can continue from a general point of view that
yes.
we're working
yes.
to a specific one?
No, it's just that I choose, I have my big momentum space.
Yes.
Okay? And of course, all P's that satisfy this condition correspond to physical quantities.
Okay.
Okay? Simply, I choose in momentum space a specific point in momentum space which corresponds to the point where I'm defining what I called renormalized coupling. So it's a choice of length in physical space, in a momentum space. It's a choice of unit.
Okay.
You see, for instance, you think of it simply by saying that I'm expressing all the momenta or all the energies either in EV or in KEV or in MEV or in GeV or, you see.
All right.
And this means that when I'm studying the theory, I refer everything to the properties of the theory when the energy involved are of the order of either the EV or the KEV or the MEV or the GeV. Okay? So this choice is mathematically, you can choose whatever you want, and if you are, as a physicist, you are going to choose a mu that corresponds to the energy scale of the process you are interested in. So if you are doing cold atom physics, you are not going to take a mu, which is the same energy scale that if you are doing experiments at CERN, at LHC. Okay? It's just that. Okay. So with that, we get this formula for GR. So you see that in the same way that the renormalized mass is not equal to the parameter B that we set that we have to set in the action, the coefficient C that we have to set in the action is different from the renormalized coupling constants, which correspond to the value of the 4-point function at the given reference frame, the reference point in momentum space for the irreducible 4-point function of your theory. Yes?
Why exactly do you need a specific energy scale dependent coupling?
The point is that you need one. You need one because you cannot, either you express everything in terms of the energy scale, which is the ultraviolet cutoff, but you want it to go to infinity. So you need another energy scale. We are in the massless theory. A massless theory is scale invariant. I'm going to discuss that a bit later.
You're just introducing a random scale so that you have something to compare it to.
Yes. We have to express everything with reference to energy scale. We are dealing with a massless theory. So a massless theory is scale invariant in momenta or in position.
Your couplings are energy dependent anyway, right?
This means that this is going to mean that the effective couplings are energy dependent. But this is going to be the result of the calculation. Okay. So you could say, aha, I knew that the couplings, the effective couplings, are energy dependent. Because we now are both as high energy physicists and as condensed matter physicists, we are used to that. But this is a non-trivial effect of quantum fluctuations. And that's what this calculation is going to show. Okay? Okay, so I define this GR like this, and if you do this, of course, now the issue is that re-express the 4-point function irreducible in terms of GR rather than C. And if I re-express it in terms of GR, remember, GR is related to C by this series expansion. So I can invert that and write C as GR plus GR squared 3/2 and the same coefficient, 1/4 pi squared log of lambda squared divided by mu squared plus term of order gr to the power 3. I'm inverting this. And I plug the initial result for C here. So I re-express everything in terms of, so I take this, and I replace C by this. And what I get is gamma 4 irreducible equal GR minus GR squared 1/2, 1/4 pi squared, okay, and the log of lambda in the numerator of the log here are cancelled by the log of lambda in the numerator of the log here, because there is a plus sign here and there is minus sign. So what you get is log of mu squared divided by P1 plus P2 squared plus log of mu squared divided by P1 plus P3 squared plus log of mu squared divided by P1 plus P4 squared plus term of order GR to the power 3. So you see, expressed in terms of GR rather than C, it is ultraviolet finite. No log of lambda anymore. Okay. There will be some logs, but they are going to push here. So this is going to be a 2 loops diagram plus some counter terms that contains logs of lambda, which may be dangerous, but so all the logs have been pushed, possible logs have been pushed into the higher loop terms. You see? So expressed in terms of GR, this is ultraviolet finite. So this makes sense. This makes sense for any momenta P1, P2, P3, and P4, provided that they satisfy the sum P1 plus P2 plus P3 equals 0. Okay. So re-expressing the 4-point function calculated with the theory with A, B, and C, the 4-point function is ultraviolet finite. So now, and now remember, this was going to be B equal 1 plus C. You see, but C is equal to G renormalized to something. So my final choice is A equal 1, B equal 0 plus G renormalized and this, and C equal G renormalized plus G renormalized squared, 3/2, 1/4 pi squared, log of lambda squared divided by mu squared. So with this choice of action, okay. So and with taking what's called the renormalized action, that's going called SR of phi, which is this integral over 4x of A over 2 d mu phi squared plus B over 2 phi squared plus C over factorial 4 phi 4 with this choice of A, B, and C, which is written here. The 2-point function, the 2-point and the 4-point functions are well defined as functions of the momenta P1, P2, etc., and GR. And the limit lambda goes to infinity exists. You see? Because it's given, the 2-point function is always P squared, and the 4-point function now is given by this big integral where the ultraviolet cutoff is not there anymore. Okay. And you see, in this, with this way to construct the theory, what you have to take is to choose a mu. Choose a value of GR. And then adjust A, B, and C as a function of lambda and take the limit lambda goes to infinity. So constructing a renormalized theory amounts to you choose mu, your renormalization scale, choose a value of GR, well, choose MR to be equal to 0, the physical mass, and physical to be equal to 0, because that's something we choose at the beginning. So, and let adjust and let lambda goes to infinity, A, B, and C being given by this explicit formula. And then you get a continuum limit, which defines the 2-point and 4-point function of the renormalized theory. Okay? Yes?
So what initially, if from the start we knew we were trying to describe massless theory,
yes?
What motivated us to even include the phi squared term in the first place? You know what I mean? Like,
I introduced the phi squared term in the beginning because I know I have to change it from 0 to something in order to keep a massless theory at one loop.
like,
If I start from an action in the functional integral, which doesn't contain this, I'm going to get a massive theory with a very high mass. You see?
okay.
You see? So that's the theory. So, and what I mean constructing the theory, it means that now if I construct a path integral out of this action, exponential of minus SR of phi, with the renormalized action defined in this way, and if I take a product of phi, and I divide by d phi exponential of minus, so the path integral, the functional integral defined with this normalized action. This define a vacuum expectation value of products of operator in the renormalized theory. So in other words, a renormalized correlation function. Okay. Here, which are given by this. So this is what I'm going to call the renormalized four-point function. Okay. But this construction depends both on the choice of mu, and on the choice of GR. Okay? Yes?
But you say you fix GR, right? So
yes.
Wouldn't continuum limit break your action?
In the continuum limit, the coefficient in the action diverge. Yes. But that's not a problem. You see, you must think of the path integral as just a mathematical recipe to construct the correlation function of a quantum theory. What's important is that this makes sense. Because out of Green's function or vacuum expectation value of operators in a quantum theory, as I stated, I think when I was answering one question 1 or 2 days ago, you can, for instance, reconstruct mathematically the Hilbert space and the Hamiltonian of the theory. So all the information we need to have a sensible quantum physics theory are correlation functions with the good properties.
So if the correlation functions are okay, but the exponent, the renormalized action is divergent,
yes.
we'll still take it.
We'll still take it, yes. Yes. You can view this just, you see, you can view this as a distribution, a probability distribution on the space of phi. And in the continuum limit, this probability distribution may become very, very singular. We have seen already at the level of the free field, although in the free field, you do not need any renormalization because G is equal to 0. We have already seen that in the free field, the typical distribution, a typical field configuration in the path integral is very, very irregular. So in the continuum limit, you cannot define it as just an integral over regular functions. So this problem exists already. You have already some singularity when lambda goes to infinity for the free field. The problems are much less severe, but they are still there, you see. So it's just an extension of the properties of the free field in the case of an interacting field in some sense. So it's much more complicated, much more subtle, because you have to take into account the couplings and the radiative correction, but it's already there. It shouldn't come as a surprise. Okay? Good. Okay, so, well, I think I'm going to end up there. And the last point will be treated tomorrow. I think it's good because that's a very important point. Just what I wanted to show you as just an introduction to what I am going to do next week, tomorrow, is that, well, you may ask, you may say, okay, but we started from a theory that depends only on one parameter. The classical theory depends on the coupling constant, G. And the quantum theory depends on 2 parameters. So classically, we have G. Classical theory, it depends on the coupling constant G. And the quantum theory, it seems to depend both on mu and G renormalized. So the quantum theory has added seemingly an additional parameter. So it seems that we may construct different quantum theory with the same renormalized complete constant and a different mu. And we are going to see that, in fact, so we have one parameter. Are there two parameters? We are going to see, in fact, simply already on this expression, that this is not the case. That, in fact, basically, if we write GR here and mu as a two-space parameter, different choice of GR and mu may correspond to the same theory. And we are going to see that explicitly, the same quantum theory. Because, and we are going to discuss this very important effect and property of the quantum theory tomorrow. So in fact, there are no two parameters. There is only one parameter that labels the different quantum theory we can construct by path integral. Okay?